Hello everyone and welcome back to another video. Today we're going to get started with the RF1 to 8 outcome, that is relations and functions, and function notation. So some of the key ideas in this outcome include being able to interpret and explain different types of graphs, data, and situations. We want to be able to understand the difference between relations and functions and understand how to identify them, as well as being able to represent a linear function using what we call function notation. Another thing that I also want to add on as well that's extremely important in this outcome is being able to identify the domain and the range of functions and relations. And we'll talk about that very shortly. Now we have a whole bunch of relationships in our everyday lives, including between our friends, family, teachers, coaches, and so on. But in math, a relation identifies a relationship between two different things. So more specifically in math, a relation tells us about the relationship between two values. So more specifically, how an x value is related to a y value and vice versa. Relations are often expressed in things that we call ordered pairs, and we call them ordered pairs because the order of the numbers that appears is very important. So we'll take a look here at our first example. An ordered pair is always expressed in the form xy, which means that your x value will come first, followed by your y value. So in the ordered pair 3, 5, the x value of 3 is related to the y value of 5. We can group these ordered pairs into something called sets using set notation. So we use curly brackets or curly braces to show that something is part of a set. So this set here, and the set of the ordered pair is 1, 2, 2, 4, and 3, 6, represents a relation with 3 ordered pairs, and we can also show these 3 points on a graph. So we can also express relations in 5 other types of formats. The first one being a table of values that you guys have already talked about in junior high. So looking at each of our ordered pairs here, we can go ahead and identify all of our x values. So we know that 1 is an x value, our 2 here represents an x value, and then the 3 there. And then we can go ahead and identify all of the y values that are associated with each of those x values. So let's go and fill in our table of values. We've got 1, 2, and 3. And we can take a look here and see that the x value of 1 is related to a y value of 2, an x value of 2 is related to a y value of 4, and finally this x value of 3 is related to a y value of 6. We can also use what is known as a mapping diagram to express the same set of data. Now, to use a mapping diagram, all we need to do is simply plug in all of our x values into this little bubble on the left-hand side. So we've got 1, 2, and 3 here. And then finally, for the corresponding y values, we have 2, 4, and 6. Now, the reason why we also call mapping diagrams arrow diagrams is because of the fact that we simply need to draw arrows showing how one value is related to another. So the 1 is related to the 2 is related to the 4, and finally the 3 is related to the 6. Now, typically we don't use mapping until the 30 level, and you guys will learn something called mapping notation at the 30 level. For the time being, we're perfectly fine calling these arrow diagrams. Now, something to note, if a number occurs more than one time, it only needs to be written once. So for example, let's say I add another data point into this set. So I've got 2, 7, for example. Instead of writing another 2 here, all I need to do is simply add a 7 down here, and I can express that the 2 is related to both the 4 and the 7. Now, the third way that we can express the same set of data is by using a graph, something that most of you guys are already fairly comfortable with. So we can go ahead by writing our scale down here. So I'm going to go 1, 2, and 3 down along the bottom because we know this is our x-axis. And up here along the top, our vertical line will be my y-axis. So I'm going to go 1, 2, 3, 4, 5, 6, and then I'm trying to freehand and make sure that my scale is about as even as I can get it. So we know that an x value of 1 is related to a y value of 2, so I'll go ahead and plot that down here. An x value of 2 was related to a y value of 4. And then finally, an x value of 3 was related to a y value of 6. Now the question that we need to ask ourselves is, do we connect each of the points or do we not? And we're going to answer that on the next page. So how do we know if the points get connected? It just depends on the data type that we're looking at. So there's two different types of data that we explore. The first being discrete data, where there's no line that we draw through the points. And the second type of data being called continuous data. Now the differences between these two lie in what happens in between the points. For example, in discrete data, only the given points are possible. Nothing between or beyond them is going to be possible. In continuous data, anything between or beyond is going to be possible. And we'll take a look at a couple of examples. One of my favorite types of food to eat is pizza, so it's no surprise that I know a lot about pizza toppings. So one of the examples we're going to use is pizza toppings. If I add one extra pizza topping, it could cost me $2. If I add 2, it's going to be now $4, $3, $6, and so on. So why would this be considered discrete data? Well, if we think about the number of pizza toppings, is there anything that exists between 1 and 2 toppings? Can I have 1.1 toppings? Can I have 1.9 toppings? Can I have 1.748 toppings? And the answer would be no. We can't have anything between 1 or 2. So that would make the number of pizza toppings that we add a discrete type of data. A second type of example would be maybe the number of customers that go shopping per hour at a mall. We would only be able to have, for example, either 30 or 31 or 32 customers, and it makes sense because we can't possibly have 0.1 of a customer or 0.5 of a customer. As for continuous data, there are a number of naturally occurring examples, such as the temperature of Calgary as time passes on. So for example, if we think about the time between 1 and 2 minutes, it's entirely possible for us to figure out exactly what the temperature is at 1.0001 minutes or 1.985 minutes. We could also think about the height of a skydiver as they jump out of an airplane. Now in this case, along the axis would be our time, and we can ask ourselves, between 1 and 2 seconds, would we be able to track their height as they're falling out of the plane? And the answer would be yes. At 1.7 seconds, we could say that they are 1,000 meters above the ground. At 1.72 seconds, they are 982 meters off the ground, and so on. Now, the key to identifying the difference between discrete and continuous data is to ask yourself, is it possible for there to be more data in between the points that are given to me? The fourth method that we can use to represent different types of relations is words. So we know, again, from our examples, and maybe I'll write them down as a quick refresher here, we had a set of numbers of 1, 2, 2, 4, and 3, 6. We can see that every time we increase in value our x, every time we jump up 1 for x, we actually double whatever that x value is. So we can say that the second element y is going to be double the value of our first element x, and this is how we would represent this type of relation in words. We can do the same thing in a mathematical equation. With y is equal to 2x, all we are saying is that if we double our x value, then we would get a y value. Let's take a few minutes here to practice some questions. You guys can go ahead and pause the video and try these out at your own pace. When you're ready, go ahead and unpause the video. So looking at our first example here, we have a set of ordered pairs that we need to express as a table of values, a mapping diagram, as well as a graph. So going ahead and starting off with our table of values, we know that we've got our x values here on the left-hand side, and then we've got our y values on the right-hand side. So if you haven't already done so, we can go and identify each of our x values here. We know that our x values will be the first number in each ordered pair, and then the y value will be that second number. So we can take all of our x values and plop them into our table here. So 1, 2, 3, and 4, followed along by their related y value. So the 1 is related to the 4, the 2 is related to the 5, the 3 to the 6, and the 4 to the 7. So a question that I get asked often is, how do I know what order to put my values in? And usually what I tell my students is your x values will always go from least to greatest. That's the way it's going to look on your graphing calculator and most data that you're going to look at. Now for your y values, that's not the case. Remember that your y value depends on whatever x value you have. So I can't necessarily say that I'm going from least to greatest for my y values. I'm really just following along with whatever x value each y value is related to. So if I go least to greatest for my x values, it doesn't necessarily mean that your y values will also go from least to greatest. This is just the data that we're working with. For your mapping or arrow diagram, let's go ahead and draw our two bubbles here. So you've got your enclosure for your x values, one for the y values. We can pop those numbers into here, 1, 2, 3, and 4. And same thing for your y values, 4, 5, 6, and 7. And we can go ahead and show how they are related to one another. Looking at your graph now, let's go and label our x and y axis. We can start off with our origin here at 0. We're going to go 1, 2, 3, and 4 along the bottom. And then maybe let's go up by 2s along your y-axis. So you got 2, 4, 6, and 8. So we can plop our points down here. 1 is related to 4, 2 is related to 5, 3 is related to 6, and 4 is related to 7. Now again, let's be careful because this data would be considered discrete. We don't know for sure if there's anything in between them, so we are not going to connect our points. In our second example here, you'll notice that our ordered pairs are not in order from the lowest x value to the greatest. So let's go ahead and label all of our x and y values first. And let's set up our table of values. So for all of your x values, let's go least to greatest. So we've got 2, 4, 6, and then 9. So 2, 4, 6, and 9 will come into that x column. And we look at our related y values. So 2 was related to 3. The 4 was related to a 2. The 6 was related to a 3. And the 9 was related to a 1. So something to note here, even though we have the same y value 3 and 3, we can't simply leave it blank, or we can't simply only have one 3 here. We have to make sure that each x value is connected to a related y value. So you can see here we have 2 connected to that 3, and the 6 here is connected to this 3. It's still the same 3, but we need to show the relationship between the two values. As for your mapping or arrow diagram, we can go ahead and start to draw these in here. So we can put our x values in, 2, 4, 6, 9. So I'm just going least to greatest. And then for your y values, I am actually going to go from least to greatest as well, 1, 2, and 3. Note that in this case, the order doesn't really matter because again, we're going to be drawing arrows from one value to another, which is very different from your table of values here. And since we have 2 of the same 3, I only write the 3 once. So let's go ahead and show how these values are related. So the 2 comes down to the 3, the 4 goes to the 2, the 9 goes to the 1, and then the 6 goes to the 3. Last but not least, we're going to graph these values or these data points. So you've got our X and Y axis labeled there. I'm going to start off with a 0 at the origin. And then let's decide to go up by 2s. So 2, 4, 6, and 8 along the bottom. Then along the side, let's go up by 1s. 1, 2, and 3. So plotting our first point, we know we've got 2, 3, which is going to be here. We've got 4, 2, which is gonna be down here. 6 is matched up with 3 up here, and finally 9, which would be somewhere maybe over here. What I should actually do is write down my last portion there. I've got a 10, so I've got my 4 points plotted on a graph. And again, since we aren't sure if there are actually data points in between, for example, the 2 and the 3, I cannot connect these. I cannot simply assume that there is actually data in between what is given to me. So now we're going to talk about the difference between functions and relations. Now functions act as a special subset of relations, which means that every function is going to be a relation, but the opposite won't be true. We can define a function as a special type of relation where every x value only has one y value related to it. In a mapping diagram, we're able to figure out if a relation is a function because every x value will only have one arrow relating it to a y value. So you can see in this example here that each of these x values only has one arrow coming out of it. So we can see here we've got one arrow coming out of the 0, we've only got one coming out of the 1, a single arrow here, and a single arrow over here. Same thing with the mapping diagram on the right hand side. Even though they're all pointing towards the 6, we still only have one arrow per x value. On the other hand, if we take a look at some examples where this is not the case, we can see that in this example that the 5 has 2 arrows coming out of it, which means that this x value of 5 is related to 2 values of y. Same thing with the 3, it's related to the 3 here and the 2 down here, and then the -2 is related to both the 1 and the 0. For this bottom right relation, we can see that this -2 is related to 3 separate y values, which is not allowed if it's supposed to be a function. So once again, something to keep in mind is that every function is a relation, but the opposite's not necessarily true. Not every relation is a function. Now you might be wondering, why do I need to know what the difference is between a function and a relation? Well, if we take a look at a quick example here, and this is a bit of an extension, if we think about some of the implications of something being a function versus a relation, we can look at this very quick example. If, for example, we have a time versus temperature graph, and then we've got our time in, let's say, seconds here on the bottom, and then perhaps in Celsius on our y-axis, so we're starting off at 0. Would it be possible for us to have 1, 2, 3 separate temperatures at 1 second? Now think about that. Would I be able to have at 1 second maybe 2 degrees, 5 degrees, and 10 degrees here? And the answer to that is no. We wouldn't be able to have 3 separate temperatures. So let's put some numbers to this. We've got 2 and 5, and let's say a 10 here. And we can see, again, from our mapping diagram that I'm about to draw, if we look at our x values and we compare them to our y values in a mapping diagram, I've got an x value of 1, and I've got my y values of 2, 5, and 10. We can see here that this singular x value is related to 3 separate y values, which makes this a relation. So again, there is a practical application of this. It shows us that this can't really exist in a day-to-day situation. Now, a visual way to figure out if a relation is a function is to use what we call a vertical line test. It's a very simple test that we can use for any type of graph where we're unsure if something is a function or a relation. So how do we use it? First of all, we can draw a vertical line through any point of a relations graph. If it touches the graph more than one time, it shows that 2 values of x, or rather y, are related to a particular value of x. So therefore, the graph is only a relation and not a function. So let's try out a couple of examples together. So let's say I draw a line right here where x is equal to 1. And we can pinpoint all the different times where that vertical line crosses the graph. So we can have one there, crosses there, and crosses there, and it crosses there. We can see that it fails the vertical line test. It passes through more than one time. So therefore, this is an example of a relation. Now, if we think about our definition of a function again, for one particular x value, it can only relate to one y value. And we can see that's obviously not the case here. We have one x value related to 1, 2, 3, 4 different y values. Taking a look at example B, once again, let's go ahead and draw a vertical line through this graph. And we can see very quickly that regardless of where I draw this line, I could draw it here, I could draw it right here through the middle, I could draw it here, it would only pass through once, making this relation a function. So let's go ahead and say that it's a function. Over in example C, again, we can see pretty quickly that we're going to end up with a function, because again, if I drop this line anywhere, we can see that it only is going to pass through that pink line only one time. One last example. We can take a look over here for question D. We can see that this is going to be a relation because it's going to pass through this graph at 2 different points. So let's go ahead and fill the rest of this in. We know that this is a relation. We said that this was a function, and we can take a look at some of our other examples. So a few of these are a little bit trickier, but we'll take a look. If I draw a vertical line through here, we can see very quickly again, this will be a relation because it crosses through at 2 different points. Now this one here is a little bit interesting, because I'm sure a lot of you guys will be asking, well, what happens if I draw my line, and maybe I'll draw one that's a little bit more vertical. Let's draw this line here. Some of you guys will be wondering, well, what happens if I put that line right here? And you say, well, it's gonna pass the vertical line test, it only crosses once, and that's absolutely true. But you need to remember that the vertical line test should work on really anywhere for this graph. So even though it works here, it doesn't happen to work here, it doesn't happen to work here, or really anywhere within this boundary here, and it doesn't really work anywhere after this point either. So there's only really one point where it works, but because it doesn't work at a second location for this graph, then the whole thing still remains a relation. Again, we'll see very quickly here that this one will be a relation. And now the last one gives us a very interesting situation here. When we consider a straight vertical up and down line, we want to imagine, and we're minimizing the problem here. I want to start off with a single point. And I try my vertical line test and I say, okay, well, that's great. It only passes through once. This is a function. Now, let's go and add a second point right above it. And we can see again that if I draw a vertical line through there, it ends up being a relation again. And let's maybe add a third, fourth, fifth point. And we can see that when we start to add continuously more points along there, what would we end up with? We'd end up with a line. So a line really is an infinite number of points. So if I drew a vertical line through an infinite number of points, well, then we're touching this graph at an infinite number of points. So this would then make this a relation. Now let's try looking at a few sets of ordered pairs to figure out if these are functions or relations. There are a few different methods you can use to determine this. First of all, we can actually, and this is probably the quickest way when we're looking at a set of ordered pairs, we can look at all of your x values. So we can see here, we don't have any repeating x values. So right away, we can actually state that this is a function. Let's go ahead and write that this is a function. So how does this work? Well, again, that's the quickest way to do it. We don't have any repeating x values, which means that there is no single x value that's related to more than one y value. If we decide to use a mapping diagram, and we know we've got 2, 4, 5, and 9, 2, 4, 5, and 9. And the corresponding y values are 3, 4, and 10. So 3, 4, and 10. And we can go ahead and connect our values to each other. So 2 is related to 4, 4 is related to 3, 5 is related to 10, and 9 is related to 4. So we can see here that each individual x value is related to only one y value. So again, we've proved that this is a function. You could also graph all of the points, and we'll see that, and maybe we'll do a really quick sketch. So you've got 2, 4, 4, 3, 5, 10, it's up around here, and we finally have 9, 4. So 9, 4 is over here. So we can see very quickly, again, that if we drew a vertical line anywhere on this graph, it would only pass through once, or at most one time. Now, on the other hand, if we look at the second example, we can start off with our first method. We're going to look at all of the x values. If there is a repeating x value, we're in trouble. So we'll see here that we have a repeating x value of -2. So we have a -2 and a -2, which means that we have a relation. So let's go ahead and prove it. If we have, again, and we'll shorten this a little bit. If I looked and only considered my 2 points here, I have -2, 9 and -2, 3. We can see right away that this singular x value is related to 2 separate y values. So we can say that -2 is related to more than one y value. And for the right hand side, I realized I forgot to write down our justification here. there are a couple different ways we can express our answer. We can simply say that each x value is only related to one y value. Or alternatively, you could say that the graph passes the vertical line test, which means that it only passes through once at most. So on this page, you guys can feel free to pause your videos and take a few minutes to work through these problems on your own. When you are ready, you can unpause and check your answers. So this first one here is very clearly a relation, because if I draw a vertical line through any part of this graph, it will pass through twice. So we can say that this is a relation. Our second example, we can quickly check our x values. We see that you have no repeating x values, which means that every x value is only related to one y value. So this is a function. For problem C, we can take a look here and we'll see that the value of positive 2 is related to multiple y values, which is not allowed in functions. So it must be a relation. And this graph here on the right hand side is actually the graph of this same relation here on the left. And if we draw a vertical line through those points, we can see it crosses 3 times, making this a relation. Now the next portion here, domain and range, is probably one of the most important sections of Math 10C. Not just because it's quite difficult, but because of how often you will use it in grades 11 and grade 12. And it's really important because it helps us set boundaries on what values are and aren't allowed. Now we can go ahead and define the domain of a relation as all of the possible x values within that set. So all of the possible x values within that set. And we typically use x as our independent variable. And you guys will talk about that usually in science. Now on the other hand, the opposite of the domain is what we call the range. Now the range describes all of the possible y values within that set. And we typically refer to y as our dependent variable because it depends on whatever happens with x. Now within a set of ordered pairs, we can quickly figure out what the domain and range is. And remember that this is discrete data because we only have these 4 points. There is a pattern, but we aren't 100% sure that there are points in between them. So we can express your domain and range as follows. Now before we do that, let's go ahead and identify all of our x values in each of these. So we have x values of 1, 2, 3, and 4. And then we have our y values of 4, 5, 6, and 7. So we can gather up all those values and put them into a set using the curly brackets. So we have our domain as a set of 1, 2, 3, and 4. And the range is the set of 4, 5, 6, and 7. Now, like I said earlier, figuring out the domain and range of discrete data is fairly simple, but it does get trickier when your data is continuous. So taking a look at this first example here, we'll notice that we have a curved line going from here until here, and we go between here and here. So what we want to identify is first all of your possible x values that actually exist, right? We're not looking at what your boundaries are from the size of the graph, so we're not actually moving on until +4 and -4. We're only looking at values of x between -1 and +1. Now on the other hand, if we're looking at our y values, we're looking at anything that goes from 0 up until +1. Now how do we express this in terms of domain and range? So we can describe the domain above using set notation. So in plain old English, this whole thing reads as the domain is the set, and we denote the set with the curly brackets, the set of all x values such that, so this longer looking line here really just means such that, so we'll write that down in case you forget. So this means such that okay, so the set of all x values such that x is greater than or equal to -1 and is less than or equal to +1, and x is an element of the real number system. Now that's a lot of things to remember, but we want to break it down very slowly. So once again, we're looking at the set of all possible x values, and we know from our visual up here that all of the x values that exist go between -1 and +1. So we're just saying that x is in between -1 and +1, and it can equal to both -1 and +1. We can tell because there's definitely a point there that exists when x is equal to -1 and when x is equal to +1. Now the last part here does give students some troubles. Why do we need to express that x is an element of the real number system? Well, there's a couple reasons for that. We're not only looking at whole numbers such as -1, or rather, we're not looking at integers such as -1, 0, and 1. We're also looking at things such as decimals, we're looking at square roots, which means that we can have numbers such as the square root of 0.224. We can have numbers like -0.5 that will exist because we're stating that this is a condition of any x value in between -1 and +1. We can use a different example just to make it a little bit more clear. We could use an example where we say that every person in the classroom has to be a student. That would be essentially what this portion here is representing. So we have a whole bunch of students. Now we have a secondary condition that narrows it down a little bit more. Where are these students from? Well, these students can only be from Calgary, and that's a different way of looking at it. So now we're saying these students can only be from Calgary. Well, could we put a different type of condition on it? Sure, let's say that these students can only wear glasses. So only students who wear glasses. And that's what this symbol is going to help us with. So we have learned about the real number system already in a previous outcome. Now let's say, for example, that we said we're only allowing integers. If we only allow integers, this will actually change our graph quite a bit. We would only see points that go here, here, and here. We would have nothing in between because we're saying that x can only be integers between -1 and 1. Well, you only have 3 integers within those boundaries, -1, 0, and +1. So you need to be really careful in understanding what this section means. Now, one thing that I forgot to mention, this guy here means we're looking at an element, or otherwise known as a part of the real number system. Now moving on to your range, we'll see here that again we're using set notation, and we can read this out as the range is the set of all y values such that y is greater than or equal to 0 and less than or equal to 1, and y is also an element of the real number system. So we've been talking a lot about set notation, but a different type of notation that we can use is called interval notation. We can express the domain and range from the previous example as the following. We see here that we have D is the interval that includes -1 all the way to +1. And the range is all of your values with 0 and 1 inclusive. We use the square brackets when those n values are included, and we use round brackets when they're not included. Now that might not seem like it makes a lot of sense, so let's go ahead and provide a visual example. If I draw a number line here, and I put the numbers -1, 0, and 1, this interval notation on the left tells me that I'm going to include the value of -1 along with all of the values between -1 all the way up until +1, and I'll also be including +1. So that's my domain here. Same thing goes for my range. If I go ahead, let's go from -1, 0 to 1. In this case, because we are starting at 0, I'm going to go ahead, draw a circle here and fill it in. And we're going to go all the way until +1. So our endpoints are at 0 and +1 with those values being included. Now let's try it out with your round brackets if the values were not included. So let's say, for example, that your domain now goes from 0, that's not included, all the way up until +3, and we are going to include that. And your range is going to go from, let's say, -1 up until +2, but we're not going to include +2. So let's draw a small little number line here. We're going to go from 0, 1, 2, 3 for the domain. And if we take a look at the range, let's go from -1, 0, 1, and 2. So starting off with your domain here, we can see that we don't include the 0 because of that round bracket there. So I'll draw a circle there and not fill it in. We are going to go all the way up until +3. We're going to include all the values in between. And we can see that we are including +3, which means that I can draw a circle here and fill it in. Now the difference again between these two is that I do not fill in the circle for 0 because there is no value of 0 here that exists, but we do include 3 with our domain here. Now for the range, we are going to include the -1, so I'm going to go ahead and draw a circle, but I'm going to fill it in this time. We're going to go all the way up until +2. And we'll see that because of this round bracket, we are not including the +2. So I'm going to draw a circle and not fill it in. I'm going to leave it an open circle to show that the 2 is not included in this range. So typically in grades 11 and 12, most math teachers will use set notation, but interval notation is just another neat way to express the domain and range of a function. Now if we take a second here and think about the domain represented by the set of all x values, such that x is an element of the real number system, how would we be able to express this in interval notation? And why do you use your choice of bracket? Take a few seconds, think about what your answer is, pause the video, and then unpause once you're finished. So in this case, it would actually make the most sense for us to look at our domain as the interval from -infinity to +infinity. Now, why would we use round brackets instead of square brackets? Well, let's look at the difference between the two. So let's imagine that we wanted to include -infinity and +infinity as our end values. Would we be able to define a final value for -infinity or +infinity? For example, think of the largest number you can and then add 1 to it, and then add 1 again. That largest number that you just thought of can become infinitely larger even if you just continue to add 1. So in this case, we can't actually put an end to infinity, so we would not be able to use the square brackets. We would have to use the round brackets. So let's try out a couple of practice problems together. In example number 1, we see we're comparing the fruit to its color. We can see that we have apples, blueberries, cherries, and huckleberries, and we have the colors red, green, and blue. Our first task is to figure out if the data is continuous or discrete. In this case, it's going to be discrete data, and the reason is that there's no continuation, there's no spectrum between colors or fruits. There's nothing in between an apple or a blueberry, it's either or, and in this case, we're not really looking for anything between red and green or green and blue. The independent variable in this case, we are going to be looking at our fruit. And the dependent variable is going to be our color, because our color depends on what type of fruit we are choosing. So for our domain, if I start over here to give myself a little bit of room, it is the set of our apples, blueberries, cherry, and huckleberry. If we look at the range, it's going to be all of the possible colors, so red, green, and blue. Now note here I'm using set notation because I am just showing that it's the set of all of these included values. So that's why I'm using set notation rather than just listing the range in this case. I'm going to skip example number 2. We're going to move on to example number 3 here. And we can see here we have 1, 2, 3, 4, 5, 6 different points. Our first task again is to figure out, is this continuous or discrete data? We know it's going to be discrete data. And the reason why is we are looking at 6 ordered pairs. We have 6 points that would be on a graph. We aren't actually sure if there's anything in between them. All we have is the 6 listed data points in front of us, so we can't really make any assumptions as to whether or not it's continuous. So our best bet is to state that it's going to be discrete. Looking at the independent variable, because we don't have any context in this case, it's just going to be our x. Our dependent then is just going to be the y. So if we look at our domain, we're looking at all of our possible x values. So if I go ahead and label all of our x and y's, so in each ordered pair we have x, y, x, y, x, y, x, y, and so on. I can go ahead and list all of my possible x values. Typically, we'll go from least to greatest. So we see here that we have 0, 1, and 2. So it's the set of 0, 1, and 2. And then for our range, we have 1, 2, and 3. So our set of 1, 2, and 3. Example number 4 is a little tricky. We haven't talked about linear functions or linear equations just yet, but we want to be thinking about what happens if we were to take a table of values and start looking at different values of x and y. Well, let's look at y is equal to 3x. We'll talk about f of x later on. But if we look at y is equal to 3x, let's think about what this relationship means. We can take any x value and we're going to multiply it by 3 to give us our y value. We need to ask ourselves, can we put in a 0 here for x? Sure we can. Can we put in a 1? Yep. Can we put in a 2? Can we put in 2.5? Can we put in square root of 5? Can we put in pi? And the answer to all of those would be yes. So in this case, depending on what value I put in here for x, y can really be anything. So if y can be anything, well, that implies that x could also be anything. So that means for us that this set of data would actually be continuous. Again, our independent variable will be x, independent will be y. Our domain, like we said earlier, x can be anything. So the way to write that x can be anything in set builder notation or set notation is that we have the set of all x values such that x is an element of the real number system. So x can really be anything is what this is representing. And same thing goes for your range, the set of all y values such that y is an element of the real number system. So in example number 5, we see that we have two unfilled or unshaded endpoints, followed with a continuous line between your two endpoints. So automatically we can say that we have continuous data. We don't have discrete data because there's always something in between any 2 points. So if I were to choose this point and this point here, there's an infinite number of points because there's a line connecting those 2 points. So there's an infinite amount of data between those 2 points. So we have continuous data. Our independent variable, because we have no context, will just be x. Dependent will be y. And now this is where the domain gets a little bit tricky. We're going to be first looking at your lowest possible value of x, and then we're also going to be looking at your highest possible value of x. So we can see here that this point corresponds to -5, and this point here corresponds to a -2. If I were to ask myself, is there a value of x that exists in between those 2 points, the answer would be yes. For example, if I asked, well, is there a point where x is equal to -4? And I'd say sure, at this point here, x is equal to -4. Is there one where x is equal to -3.1? Yep, -3.1 would probably be about here. Is there a point where you have -2.5? And that would be right about here. So we can see that we have a whole bunch of values in between those 2 endpoints, and that's what's the most important to figure out in terms of understanding the domain and range of a continuous set of data. We're going to look for our 2 endpoints first. So keeping those 2 values in mind, let's go ahead and use our set notation. So our domain is the set of all x values such that, and again, like we practiced earlier, put your x value or x variable in the middle. We're going to draw our inequalities towards the right-hand side. Place your lowest possible value of x on the left, and then place your highest possible value of x on the right. So we're going between -5 and -2. Now looking back at your 2 endpoints, we notice that these are unshaded. So we have an unshaded point here at -5 and an unshaded point here at -2. So we would actually not underline your 2 inequality signs here. And we'd go ahead and finish this off by saying x is greater than -5, less than -2, and x is an element of the real number system, as long as we are between those 2 values. If we take a look at the range now, we can see our lowest value of y is going to be down here at -4, and it corresponds with that point there. And our highest value of y is this +4, which corresponds with this point here. So again, we're going to start off with our y values, so that we have the set of all y values such that your y goes in the middle. Again, inequality signs facing towards the right. We're going to put our lowest value of y, or our range, on the left, which is -4, and the highest or largest possible value of y on the right-hand side. And then y is an element of the real number system. Again, we do not underline these because there is actually no point that exists there when y is equal to -4 or +4. So if it's unshaded, we do not underline it. Our last question on this page is also a little bit tricky. Again, we can see that we have one continuous line, so we're looking at continuous data. Out of context, we have our independent variable, which is x, and dependent, which is y. Now let's start with the domain here. So I can start off again with the stuff that we typically write down, the set of all x values, such that I'm going to put x right there in the middle. And we're going to try to look for the lowest value of x possible, and then the highest value of x possible. Now I'm going to start off with the highest possible value. And in this case here, if we're looking along our x-axis, we can see that we have points for every value of x up until we hit this +3 here. And there is going to be a point right there where x is equal to 3. So we can put that 3 there. And we're going to draw our inequality signs towards the right. And then we are going to look towards the left. Well, here we see that we have an arrow. And this arrow is implying that this line is actually, if our graph was large enough, this would continue infinitely along this path, basically. So infinitely upwards towards the top left. So if it's continuing infinitely, do we actually have a lowest possible value of x? And the answer is no. Some students might be thrown off by this point there. Well, if we see our function, or rather not our function, our relation continue on, then we'd have a whole bunch of x values that would be further to the left of -2. So we can see here that there's a whole bunch of possible points further to the left compared to that -2. So we actually don't have a lowest possible value of x, which means that we can simply leave our domain as x is less than 3. So let's go ahead and write down x is less than 3. Sometimes some teachers will also do this. This is also a possibility. Some teachers might say that x is greater than -infinity. So let me go ahead and write that down. I didn't give myself enough room. So x is greater than -infinity and less than 3. That's not as common, at least at our school, but some math teachers will do this. I'm perfectly happy if you guys simply give me that x is less than +3, and x is an element of the real number system. But wait, we're not quite finished yet. We need to ask ourselves, do we underline this inequality sign? And the answer would be yes, because there is a value of x that exists when it's 3. So we do underline this inequality for sure. Last but not least on this page, if we look at the range, we're going to look for the lowest possible value of y and the greatest possible value of y. So let's start off with the lowest possible value of y. So we can see the lowest possible value will be this -2. So I'm going to put the -2 here and the y in the middle. And we're going to ask ourselves again, well, is there a greatest value of y? And the answer would be no. Once again, because we know this goes infinitely towards the top left, there's actually no maximum value of y that exists for this relation. So we can simply leave it like this. -2 is less than y. Some people will ask, well, what happens if I want to change it around? What if I want to say that y is greater than -2? Well, this would be perfectly fine, because in either way, you can see that the inequality sign faces towards the y. Okay, so these are both equivalent to each other. And again, we need to ask ourselves, do we underline the inequality sign? And the answer would be yes, because we can see here, if we ask ourselves, does y equal, or when y is equal to -2, is there a point that exists? And the answer is yes. So we can finish this off by saying that y is an element of the real number system. So in example number 7 here, we're going to be taking a look at someone's wages versus their years worked. So we can see here along the x-axis, we have the number of years worked, and along the y-axis is the hourly wage in dollars. So if we look at the data and we ask ourselves, is this continuous or discrete? In this case, because we just have 6 different data points, it would be best to determine that this is discrete. It doesn't mean that there can't be any data points in between, but because of the fact that we're looking at 6 distinct data points, we don't know for sure that there are existing values in between them. For the independent variable, because we're actually looking at something other than x, in this case, we're looking at number of years worked, we can simply state that the independent variable is the number of years worked, which means that your dependent variable will be the hourly wage in dollars, and we can add that on. So now looking at the domain, we're going to be looking at all of the existing values, or rather the existing numbers of years worked. So you can see here there's something at 1, something at 2, something at 3, something at 4, and something at 5. So our domain is the set of 1, 2, 3, 4, and 5. For your range, we're going to be looking at the hourly wage. So we can see here we have something at $8.50, something at $9.50, $10, $11, and $12. So I'll start here to give myself a little bit of room. So we have $8.50, so the set of $8.50, $9.50, $10, $11, and $12. And that is my range. For example number 8, if we look at continuous versus discrete, we can see here there's no context. We're just looking at points on a graph. So we are looking at discrete data. Independent variable will be x, dependent is y because we don't have any context. Your domain, we're looking at all of your possible x values. So we can see here we have, starting at -4, we also have -3, -2, -1, 0, and so on. So I'm going to go ahead and list all of those values. Now you might be asking yourself, is there a shortcut to writing this out? And the answer is yes. Now the reason why I'm not explaining it in this video is because people typically tend to use it incorrectly. What I mean by that is most people will tell me, well, don't we have all of your x values between -4 and +4? So I might get something like this as an answer. Now what's the problem with this? This is everything between -4 and +4 inclusive. So would I be able to have values like x is equal to 0.5? And the answer is no, there's nothing when x is equal to 0.5, which would be right here. We can't assume that we can connect these lines, right? We only have these 9 data points. We can't assume anything in this case without any sort of context. So if you were to do this, that would be incorrect. Now, if what you did instead was, you told me that you have the set, and let's do this, the set of all x values such that x is greater than or equal to -4, less than or equal to +4, and x is an element of the integer system, then that would be correct because now you're limiting your values between -4 and +4 to only integers. If you told me it was only whole numbers, that would only cover these 5 points. So we can't use the whole number system. We have to use the integers. Let's go ahead and get rid of all this. And now we're going to do the same thing for the range. So again, I'm going to look here. My lowest value of y is 0. So we go 0, 1, 2, 3, 4. So our range is the set of values 0, 1, 2, 3, and 4. So in this next part of the outcome, we're going to be describing situations using graphs, and we're also going to be coming up with a graph if we're given a situation. So the first example here talks about wakeboarding, and we're gonna look at a graph that represents the distance the wakeboard is from the starting point. Otherwise, we're looking at how far away this wakeboarder is from the dock. Now we need to be able to describe what this wakeboarder is doing in each stage of this graph or each interval. What would be an appropriate domain and range for this graph? We'll talk about that afterwards. So the first thing that I want to do is label each interval of this graph. So we can see here that we're going to look maybe at this red section. Let's call this number 1. We've got the green over here. Let's call this 2. Let me make this a little bit neater. You got number 2 here. We can keep this section here blue. So this will be 3. To purple, let's call this 4. The yellow will be 5. Let's go back to black. This will be 6. And finally, this final portion there will be interval number 7. Now, there's no one real answer I'm looking for here. It's really, what do you see? Are you able to describe it in a way that makes sense? So in interval number 1, you can see here, maybe we'll say that you slowly leave the dock. Number 2, maybe you accelerate, you speed up quickly away from the dock. In interval number 3, you are still moving away from the dock, so you're still moving away from the dock. And then in number 4, you speed up very quickly. Again, speed away quickly. Now in interval number 5, and maybe what I'll do is I'll do this in black because we can't really see, or maybe I'll do it in a nice orange color. Actually, let's redo this one. We'll do this in a nice orange. So we can see here in interval number 5 that we actually speed toward the dock. And let me clean this up a little bit. Apparently the word toward is giving me a little bit of trouble. Toward. So we're speeding towards the dock. And then it looks like in section number 5 or interval number 5, maybe you float in one place. And then finally, in the last interval, you move quickly toward the dock again. Now, since we don't have any numbers for your time and your distance from the start, something that would be pretty reasonable, let's say, for example, if we're looking at your time, that would represent our domain in this case. Perhaps a reasonable domain would be everything, and let's use t as our variable, a set of all t values such that we are going to go from 0 minutes, maybe, up until maybe 10. All right, we're gonna have a good time for 10 minutes, and then we're gonna head back to the dock. Your distance from the start, let's call this variable d. We're gonna go between 0 and we don't know how many meters, we don't know what the scale is. We can say we're gonna go from 0 meters, I guess, all the way up until, I don't know, 500 meters out. And your distance can be an element of the real number system. So that's something that's pretty reasonable. Again, what I want you guys to do is ask yourself, why did I use 0 as your lowest value of time, and why is 0 your lowest value of distance? Well, t, your time, can we have negative time? The answer is no, so the lowest we can go is 0. And for your distance, we can't have, well, I mean, we could have negative distance, but you want to be asking yourself, where would that put you if you had a distance of -2 from the dock? Maybe you're actually back on the land. So in this case, something appropriate would be 0 when you're standing right on the dock and you're getting ready to leave it. We're going to look at a few more examples of matching up different scenarios with the proper graph. So if you look at each one of these situations, we have the height of a bungee jumper after a jump, the vertical growth of a tree, the temperature of a cup of hot chocolate as it sits on a table, and Calgary's daily mean temperature. We can go ahead and compare that to each of these graphs. So we can see in graph A, we're starting off here, we're going to go up kind of slowly, and we move quite quickly up. The only one that would make the most sense is going to be the vertical growth of a tree. If you look at graph B, we start here, and then we kind of taper downwards. So the only one that would make sense for it to start off kind of high and then taper slowly downwards would be C. If you look at graph C, we notice that we start below 0, we move up, and then we come back down. That would make the most sense to match up with Calgary's daily mean temperature. So we have D here. And then finally, we have graph D. You can see here we start up high, go down, go up, but not as high, come down, go up, come back down. The only one we have left would be your height of a bungee jumper after jumping. Let me know in the comments below if you've bungee jumped before. I'd love to try it out one day. So on this page, we have a given situation and we have to come up with a graph that accurately represents it. So Robin leaves home and travels at a steady speed of 100 kilometers per hour for 1 hour, slows down to 80 kilometers per hour for 30 minutes due to construction, then continues at 110 kilometers per hour for another hour. She stops for 2 hours for a meeting. She returns home at a steady pace of 100 kilometers per hour. Sketch a graph of each scenario. So we want to do first the distance traveled versus time. So let's start off by labeling our time at the bottom here. Tip for you guys, how do you know which one is on the x-axis, which one's on the y-axis? In grade 10 or in math 10C, I would say 99.99% of the time will be your independent variable. So this will be your distance traveled, and this will be in kilometers, and we know that your time will be in hours. So after doing that, we're going to try to figure out what our scale is going to look like. So we go for 1 hour, then 30 minutes, another hour, 2 hours, and then she returns home. So we can probably be pretty safe going up by intervals of 1 hour along the bottom here. So if this is 1 hour, 2 hours, 3 hours, 4 hours, 5 hours, and 6 hours here. Your distance traveled, we see that she travels 100 kilometers here, 80 kilometers for a little bit, 110 for an hour, stops for 2 hours, then returns home. So if we take a look, we can see that we're probably going to get up to maybe about 400 to 500 kilometers worth of driving. So let's go up by intervals of 100 here. Let's go ahead and graph this chart. So it says that she travels at 100 kilometers for 1 hour. So here, after 1 hour, she has reached 100 kilometers worth of distance. She slows to 80 kilometers for 30 minutes due to construction. So halfway in between, she only goes up to another 80 kilometers here. She continues at 110 kilometers for another hour. So we're gonna be about here. We're going from 180 all the way up to 390. So we're about here roughly. She stops for 2 hours. So between 2.5 here, we're gonna go up to 4.5. We're gonna be somewhere there still. So along that same line there. Then she returns home. So we can see here that she is 390 kilometers away from home. I'm not too worried about the end there. We don't know. We know she goes home at 100 kilometers per hour. So it'll take her a few hours to get home. So we can assume that this would be somewhere up here and we won't be able to quite finish with the room that we have here. So what I'm going to do is I'm going to go ahead and connect each of these points with a straight line. We can start off with one there. You can see it's a little less steep. We'll go up a little bit steeper. This is a flat line because she doesn't move anywhere. And then we're gonna go towards home. So in a distance traveled versus time graph, this is what it would look like. Note that because it's distance traveled, our graph will not come back down. Now, if we're looking at distance from home versus time, what we can actually do, and I'm going to cheat a little bit here, I'm actually going to copy everything that I have and put it down here. Now, why am I allowed to do that? Well, if we take a look, we're looking now at distance from home versus time. So let's change this. Distance from home in kilometers. we can see here that her distance from home, if we were to compare the two graphs, her distance from home is the same. When she travels towards work, she's at work up until 4.5 hours. Now, the only thing that changes in graph B is that instead of moving away, right, up and away, she's trying to go back towards home. So now this line would actually curve or bend back downwards. So we can go ahead and extend this line down at the same kind of slope, or steepness rather, as our 100 km/h line. In this last portion of the page, we are looking at a speed versus time graph. So we're looking at time on the bottom, speed in kilometers per hour on the y-axis. So our time, we know that we are driving for about 6 hours altogether, so we can go and do that. Apparently I can't count. So 6, 7, and 8. And then our speed, we are topping out at 110 km/h, so I don't really need anything crazy here. Let's go from 50 to 100, like so. And we are going to go ahead and start off with our first couple points. When she's at home, she is not really moving anywhere. So her speed is at 0 hours. Now, as soon as she leaves her house, she doesn't necessarily go straight away to 100. We would not start off right there. She does not start off at 100 km/h at 0 hours. So we cannot do that. What we can do is we can put a point very, very close here, which is basically, it's going to end up being a vertical line. And we know she drove at 100 km/h for about an hour there. Then she dropped down to about 80 km/h for half an hour. Then she drove an hour at about 110 km/h. She stops for 2 hours. So from 2.5, we're going to 4.5. But she is at 0 km/h. And then she drives at 100 km/h going home after that. So we're going to be somewhere there. Let's go ahead and connect our points. So again, this is basically a vertical line up there from 0 to 100. We cruise at 100 km/h for 1 hour. We're going to kind of drop down to 80 km/h. We're going to go back up to 100 km or 110 km/h rather. We come down to 0 because we stopped for that meeting. And then we're going to speed back up to about 100 km/h. My notebook keeps kind of making this a vertical line. It's not exactly a vertical line, but it's close enough. So she goes at 100 km/h until she gets home. So the last topic of discussion in this outcome is something called function notation. It's really just a symbolic way of showing that the relations equation is also a function. If we look at our first example, y is equal to 3x plus 4, we can also write it like this. We read it out as f of x is equal to 3x plus 4. So there's a few key points regarding function notation that we need to keep in mind. So when f of x is equal to 3x plus 4, the function's name is f, and the variable that we're using is going to be x. So function notation is very valuable in the sense that we can figure out what the difference is between different functions. Let's say, for example, if we have f of x, and we might also be looking at g of x, or even h of x. We can see that f, g, and h are just different functions, and we've given them different names, but they all happen to be using x as the variable. F of x is also equivalent to y. So instead of saying y is equal to 3 of x plus, or y is equal to 3x plus 4, we can say that we have f of x is equal to 3x plus 4. Function notation is quite useful because it highlights the idea of the input and the output of a function. Now the input for us is always going to be our x value, otherwise known as our independent variable, and our output, which is going to be our y value, which we know to be our dependent variable. Now we'll get to what it means by input and output a little bit later on. One last thing regarding function notation is that it does not mean that f is multiplied by x. So we're not taking the f here and multiplying it by a value of x. We're not doing that. So let's jump ahead into our first example. So here it asks if f of x is equal to 3x plus 4, we need to find what f of 4 is. What this function notation is asking us is it's saying, okay, 4 is going to be our input, and we're trying to look for what the output is. So we're saying, if we put 4 into this function, what is our output going to be? What number is that function going to spit out? So let's check it out. So f of x is equal to 3x plus 4 is our function. We're saying, okay, instead of having an x here, we're actually going to replace the x with a 4. So what happens if I put a 4 into this function? Well, we have 3 times 4 plus 4. We know that 3 times 4 is equal to 12, and 12 plus 4 is equal to 16. So f of 4 is equal to 16 is what we end up with. And what that means is that when x is equal to 4, y is equal to 16. And that actually gives us an ordered pair of 4, 16, which we can actually put on a graph. If we explore maybe one more point, if we have f of negative 2, and we're given this same function up here, all we're doing is we are saying, okay, instead of having an x in this function, we're going to replace it with a negative 2. So we're seeing what happens if I put in a negative 2 into this function. So I've got f of negative 2 is equal to 3 times negative 2, which is a negative 6, plus 4. And we know that f of negative 2 then is equal to negative 6 plus 4. Negative 6 plus 4 gives me a negative 2. So what this means is that I have a point. The point negative 2 exists on the graph. So on this page, you can go ahead and try out A and B on your own. Pause the video and unpause once you're all done. We're going to explore C a little bit later on. So in A, we're given the following. F of x is equal to 3x minus 8. So we're saying what happens if I put a 2 into this function here. So if we can start off by saying f of 2 is equal to 3 times 2 instead of 3 times x minus 8. So f of 2 is equal to 6 because 3 times 2 is 6 minus 8. So f of 2 is equal to negative 2. So we can basically state that our input of positive 2 gives us an output of negative 2. And all that really means for us is that the point 2, negative 2 is a point on the line, or a point on the graph of 3x minus 8. If we take a look at f of negative 6, we're saying what happens if I plug a negative 6 into this function? So f of negative 6 is equal to 3 times negative 6 minus 8. So I got f of negative 6 is equal to negative 18, because 3 times negative 6 is negative 18 minus 8. So once I simplify this, negative 18 minus 8 is equal to negative 26. So I actually end up with a point of negative 6, negative 26 that exists on my graph of f of x is equal to 3x minus 8. Now C is actually the reverse of what we've been doing. Here it says we need to find x if f of x is equal to 16. Well, what that means is that we're given the output. The output is 16. Our input is what we're trying to find out. So what we can do is we can think of this as If we're comparing f of x is equal to 16, we also know that our original function was f of x is equal to 3x minus 8. Well, f of x is equal to 16, but f of x is also equal to 3x minus 8. So we can think of this in a couple different ways. It just really depends on how you like to interpret things. We know that because f of x is equal to 16, that means that this is the same f of x. So I can then state that f of x, which is 16, is also equal to f of x, which is 3x minus 8. I've basically just made these two equal to each other. If you're having troubles following along, we can think of it like this. If I know that a star is equal to a triangle, and then I tell you that a triangle is equal to a circle, well, what's the relationship between the star and the circle? Well, it just really means that I can also equate the star to the circle, which is exactly what we've done here. F of x is equal to 16, and f of x is equal to negative, or rather 3x minus 8. So I can make the two equal to each other. So I know that this output has to be equal to this function. And essentially what we're doing here is we are solving for x. Now, solving for x is a topic covered back in junior high. So if you need a quick refresher, you can click on the suggested video at the top right of your screen. So let's go ahead and isolate for x, or put x on one side by itself. So we're going to be using reverse BEDMAS. So step number 1, we're going to add 8 to both sides. So we'll end up with 24 is equal to 3x. And then let's move and get rid of some of this stuff over here. So let's get rid of all of this. And let's bring our work over here. So we said 24 is equal to 3x. To get rid of the 3 here, we're going to divide both sides by 3. We'll get rid of that. And we'll divide the left side by 3 as well. And we know that 24 divided by 3 is 8. So this tells me that my input is going to be 8 when I have an output of 16. So I can essentially say that I will have a point of 8, 16 on my graph. Now there's a way to check our work to make sure that's correct. Let's verify. And we verify by plugging in this input that we found to figure out if 16 is actually what the output is. So I've got f of 8 is equal to 3 times 8. So we're going to plug this into the original function that we have up here. So instead of 3 times x, we now have 3 times 8 minus 8. So we have f of 8 is equal to 24 minus 8. And we'll see very quickly here that if we put in 8, then we get 16 as an output, and we can verify our work. For this next example, you can pause the video and unpause once you're all done to check your work. So for 3a, we're looking at an input of -3. So we're going to plug in a -3 into this function here, which means that instead of having 2x squared, we have 2 times -3 squared plus 1. So f of -3 is equal to 2 times 9. So remember, we're going to work with BEDMAS, so our exponents will come first before the multiplication. So -3 times -3 gives me a positive 9. And then I'm going to go ahead and simplify. 2 times 9 is 18, and 18 plus 1 is equal to 19. So this means that I have a point at -3, 19. For 3b, we can go ahead and I'm just going to go ahead and put f of x is equal to 2x squared plus 1. And again, all we're going to do is we're going to say, okay, if this is equal to that, and this is also equal to that, then all I need to do is say that this is equal to this. So I'm going to go ahead and write that down. 9 has to be equal to 2x squared plus 1. So we're going to go ahead and try to isolate or get the x by itself here. I'm going to do that by subtracting 1 from both sides. And I'll end up with 8 is equal to 2x squared. I'll divide both sides here by 2 to get rid of the 2 here. And and I'll end up with 4 is equal to x squared. And then I'm going to square root both the left and the right hand side, and I'll end up with 2 is equal to x. So we're just going to, for those of you who are wondering, well, isn't there actually 2 answers? And you're correct, we would actually get positive and negative 2. If you're not entirely sure why we have 2 answers, that's all right. In grade 10, we mainly focus on the positive square roots of a number. So we'll just take it as a positive number, x is equal to 2. We can check our work if we want, so we can check by saying, all right, we've got f of 2, let's check it out. 2 times 2 squared plus 1. So we get 2 squared, which is 4. So 2 times 4 plus 1, which gives me 8 plus 1. So f of 2 is equal to 9. So we have done that correctly. So the last example here that we're going to take a look at talks about a monthly cell phone plan that has a monthly fee of $20 plus 15 cents a text to those not on your favorite 5 list. Now this question might seem a little archaic to you guys who are on a monthly phone plan with unlimited everything. So a big shout out to all the parents or tutors or other viewers who are watching this video and can really understand the struggle of having a per text fee back in the day. So the bill is modeled by the relation C is equal to 0.15n plus 20. So there's a lot of things to unpack here, but first we're going to write the relation in function notation. So what we're going to do is we're going to identify what our variable being used is. So our variable that we're going to take a look at is n. So we know that we have something of n has to be equal to our function here. Well, the name that would make the most sense is to call this c of n. Again, if you're not sure how we ended up with this, we can look at our first example. We can say we had something like y is equal to 2x plus 1. Well, we know that the variable that's being used here is x, or rather our input or independent variable is x, is equal to 2x plus 1. And we can simply say, all right, we're just going to call this function f. So y and f of x are really just the same thing. So next, we're going to have to use function notation to find the cost of sending 35 non-fave texts. Now, if we take a look at the context of this question, we know that it costs 15 cents per text. So if the 15 cents is actually represented in this relation with the 0.15, and the 20 here gives us our monthly fee of 20. So again, if you're having troubles with that connection, we know the 15 cents is represented by that 0.15, and the monthly fee of $20 is represented by this plus 20 there. So what does that mean for us in terms of solving this question? This 35 actually means we're going to be taking a look at what happens when n is equal to 35. So we can go ahead and say c of 35 is equal to 0.15 times 35 plus 20. So the cost of 35 text messages is equal to, and we have 0.15 times 35 gives you 5.25 plus 20. So we have C, or the cost of 35 text messages, to equal to $25.25. So we can write a short little blurb here. The cost of sending 35 texts is $25.25. Now next it says that the bill is $22.25. How many non-fave texts did you make? Now we need to identify a couple things here. This $22.25 is really just telling us that the cost of sending some unknown number of texts is equal to $22.25. And we're trying to find out how many non-fave texts did you make. So we don't know what the input was, but we know what the output was. So we can actually say that 22 25 has to be equal to the function that we started off with. It has to be equal to 0.15n plus 20. So in order to solve for the number of text messages that we sent, we're going to have to isolate for n. So my first step here, I'm going to go ahead and subtract 20 from both sides. So I'll have 2.25 is equal to 0.15n. And then I'm going to divide both sides here by 0.15. Divide by 0.15. I'll get rid of that there. And I will end up with 15 is equal to n. So we can say that you sent 15 texts for a total cost of $22.25. So in this last part here, we're going to draw a graph of the function showing the cost of the first 5 non-fave texts. So I have your X and Y axis here. We're going to go ahead and straighten that out. And I'm going to give this a label. Let's call this the cost of texting. That's a really simple title, cost of texting. On the bottom here, we're going to have our independent variable, our X, which was our number of texts. And then along the top, or rather the Y-axis, we're going to call this the monthly cost in dollars. So let's go ahead and start off by labeling our X-axis. So we can start off at 0 here. We know we're going to work our way up until 5 text messages. So we'll go 1, 2, 3, 4, and 5. Now we run into a little bit of a problem on our Y-axis. So we know that the monthly cost is $20, but our cost per text message is 15 cents. Well, we're not going to go up by 15-cent increments along the left hand or our Y-axis here, because that's going to be a very large graph. What I'm actually going to do is make this a broken line graph. You can draw a little squiggly line there to show that there's not a lot of information before our first data point. So this, and maybe I'll tidy this up a little bit. This little broken line tells the reader that there's really not a lot of important information before we hit the $20 mark. And actually, to keep it consistent, let's make this 20.00, because our very first text message will cost us 15 cents and will keep going up in 15-cent increments. So let's go ahead and plot our first 5 text messages. So we know that at 0 text messages, our plan will cost us $20. Even if we don't do a single thing, we still have to pay $20 for our phone plan. As soon as we send that first text message, we have a cost of $20.15. Once we send our second one, it'll be $20.30, then $20.45, $20.60 for the next one. And then finally, our cost of sending 5 text messages will be $20.75. Now, something to keep in mind here, I will not be connecting these points because there is no data in between them. I can't send a partial text message. I can't send 1.5 text messages. I can't send 2.124 text messages. I can't send 0.0005 text messages. So this only exists as discrete data. Anyways, that wraps up today's video. If you guys have any questions, please leave them in the comments below. Thank you so much for watching, and I'll see you in the next video.